We know that when light crosses a boundary, some of it reflects and some of it goes through that boundary and refracts and it bends. But let's look at this case where I have light moving through a medium that has a high index of refraction. So this would be something like water or glass. So a high index of refraction, and there's a boundary that separates that high index from a low index, like air or a vacuum. So on this side of this, I'm going to say I have glass. Up here I'm going to say I have air. Now, when light strikes this boundary perpendicularly, of course the angle of incidence is 0. There's 0 degrees between the normal and the angle of incidence. And so I have n1 sine theta 1 equals n2 sine theta 2. Well, the sine of 0 is 0. And so we're going to get 0 equals, it doesn't matter what n2 is, it's not going to be 0, it's got to be greater than 1. And so that must mean sine theta 2, and that means that theta 2 is also 0. So we can see if it hits perpendicularly, there is no refraction. It's only when it hits at an angle other than 90 that it does refract. Now let's say I have this angle. Now because it is moving from a high to low index, it's going to refract away from that normal line. So it bends like this. Okay? Now if I have it coming at a different angle, it bends further from that. Okay? And if I have it coming at an even steeper angle, it might bend just along the surface like that. And so what happens if it comes in at an even steeper angle? When that happens, we get what's called total internal reflection, and none of the light is actually refracted. All of the light bounces off. So in each one of these scenarios, I did not draw it, but there is some light that could have been reflected. We might have the reflected ray comes in this way, reflected rays this way, reflected rays this way, and finally at the end, all of the light gets reflected, none of it gets refracted. But this angle right here, where the light that would have been refracted gets refracted right along the surface, that's called the critical angle, theta c. Now let's look at how that angle is related to Snell's law, or let's apply Snell's law to that to see if we can figure out what that angle is. So that means our angle of refraction is 90 degrees. So Snell's law, we're going to apply it here. We're looking for theta c, the angle between the normal and the incident ray. So I have the high index of refraction, and I'm going to make this n1 down here since that's where we're starting, and n2 up here since that's the other side of the boundary. So I have n1 sine theta c equals n2 sine 90. Okay, that's what happens at our critical angle. And so sine of 90 degrees is 1. And so what I have is n1 sine theta c equals n2. Now I can divide both sides by n1, and I can see that the sine of the critical angle is equal to n2 over n1. That lets me know when the critical angle will occur, and so what angle I have to make with the normal for no refraction to occur but all of the light to be reflected. And this is cool and a useful property because fiber optics are thin little pieces of glass where we can shine light into them, and they're small enough and have a high enough index of refraction that as that light hits the surface, none of it goes through. It all gets reflected. And so that light can travel along this path. Even when we curve that cable, it still will reflect through there. So we can use this as a pipe for light, and we can use it to send information, and that's how a fiber optic cable works. We're making sure all that light gets reflected within the cable, and none of it is lost outside the cable.